right, let's let capital R be all of two-dimensional space. That is like the entire xy plane, the whole thing, entire xy plane. Some of you might have seen a notation that looks like this. If not, don't worry about it. So this R, regular R, is that kind of R squared. But all right, so let's do this. Find double integral over the entire xy plane of e to the negative quantity x squared plus y squared dA. Now, if you try to do the integral negative infinity to infinity of integral negative infinity to infinity of e to the negative quantity x squared plus y squared, dx, dy, dx doesn't really matter here. This is impossible. So what do I mean by this? Like off to the side, let's just give it a try. So if you look at an indefinite integral, just the inner indefinite integral, so integral without the endpoints here, e to the negative quantity x squared plus y squared, say dx, or the inner integral, what are you going to do here? I mean, you could try doing a substitution of, I guess, I'll just distribute like this, and then you're going to get, remember that here, if x is the variable, y is constant, well, y squared will differentiate to 0, but you'll get this. And then what are you going to do with the fact that there's this extra x? You don't have an x there inside the integral, and you're basically just stuck, right? So stuck. Yeah, U substitution's not going to work. Integration by parts isn't going to work. There just isn't a thing that's going to work. But the thing to note is that the entire space, the entire two-dimensional space, you can describe this R as the set of all points in polar coordinates where 0 is less than or equal to R is less than infinity. And let's just go one time around, so theta between 0 and 2 pi. Yeah, that'll describe every point. So then this integral right here is going to actually be equal to the integral, well, let's write in, so the dx dy, that's the, as before, that's the dA, and so that's going to become r dr d theta. Okay, and then let's write in our integral signs, and theta's on the outside. All right, so theta goes from 0 to 2 pi, and dr is on the inside, so r goes from 0 to infinity. All right, we'll do this, 0 to infinity, and then the thing we're integrating, the integrand, will now be e to the negative sign, and then x squared plus y squared, we can just write r squared for that. Let me just kind of push things a little bit closer here. Okay, and the whole point is, if you want to integrate e to the negative r squared r, that's going to work out. So this is going to require a substitution. U will equal negative r squared, and then du will be negative 2r dr. But check it out, you needed an r, right? I mean, the 2 is not really a big deal, but you needed an r, and there you have it. Yeah. So this is really going to work out, and we're going to end up with integral 0 to 2 pi. Due to this improper integral, we're actually going to have to write limit t approaches negative infinity of negative 1/2 e to the u evaluated at t and at 0, and then we should still copy the d theta here. So a couple comments, I guess, are in order. Why is this negative infinity? It's because t is really a u value, right? With the t right there. And the thing is, the substitution, what this does is u went from 0 to infinity. So when maybe we'll write this out. If u equals 0, or sorry, if r is equal to 0, then u, just plugging in here, is negative 0 squared, so it's still 0. Now, if r goes to infinity, then take a look at what happens to u, right? So take a huge number for r, square it, and stick a minus sign in front. U goes to, not equals, U goes to negative infinity. And so that there should, morally speaking, be a negative infinity here, but we don't do that. Instead, we have a limit as t goes to negative infinity here. This negative 1/2 we can bring in front of the limit. We could even bring that negative 1/2 in front of the outer integral, which we're not ready to do yet. So in negative 1/2, integral sine 0 to 2 pi. Before we, let's see, let's just actually write out here limit t approaches negative infinity of what? And let's just go ahead and do the plug. So the negative 1/2 has already been taken care of. But let's write in here, let's see, so we've got e to the t minus e to the 0. And e to the 0 is 1. Okay, d theta. And then let's write negative 1/2 integral 0 to 2 pi. And now let's think about what happens. Pick a large number in the negative sense for t. I mean, if you want, here's just a graph of t-axis and then y equals, I shouldn't call it y. I'm running out of w equals e to the t. Looks like this, right? Our standard exponential. And when we travel this way on it, it approaches 0. So that limit right there, 0. Yeah? So 0 minus 1 d theta. In other words, negative 1/2 integral 0 to 2 pi of negative 1 d theta. And so copying the negative 1/2, we need to integrate negative 1 with respect to theta. So that'll be negative theta evaluated at 0 and at 2 pi. In fact, let's just cancel minus sign with minus sign. So what we really have here is theta over 2 evaluated at 2 pi and at 0. And so when you plug in 2 pi for theta, 2 pi over 2. When you plug in 0, 0 over 2. So you just end up with pi. Whoa! That was unexpected, I think, right? But here's the thing. Let's go back. We actually computed this integral that seemed impossible, and it really is if you just stick in xy coordinates. But by converting this into a double integral in polar coordinates, we got that this is actually equal to pi. So here's what I'd like to do. Pi, just copy this here. Pi is equal to that integral boxed up here. Okay, we're just going to rewrite this down here because we just computed an integral that we could really never do. Let me leave the screen like this so I can copy this. Negative infinity to infinity, integral, again, negative infinity to infinity, e to the negative quantity x squared plus y squared dx dy. But now, what we're going to do is kind of an interesting algebraic manipulation. So here's the thing. This is actually integral negative infinity to infinity, integral negative infinity to infinity, and go ahead and distribute that minus sign. And, well, don't we have e to the negative x squared minus or plus negative y squared dx dy. And then we could actually rewrite this as integral negative infinity to infinity, integral negative infinity to infinity. And look, we're adding in the exponent, so this is really a multiplication of things with the same base. So e to the negative x squared times e to the negative y squared dx dy. Yeah, just standard algebra rules of when you're multiplying two things here with the same base, you add the exponents. We're just doing that backwards. Now here's the awesome thing is that what we have here is a product, and these are independent pieces. The x variable appears, the y variable appears, so we could actually factor out this e to the negative y to show up in front here. Basically, we have a product of two separate integrals. So we have integral negative infinity to infinity of e to the negative x squared dx, and we have that multiplied by integral negative infinity to infinity of e to the negative y squared dy. Now here's the funky thing, is that this integral here and this integral there, they're actually the same integral. I mean, it's just with different placeholder variables, yeah, x here, x there, versus y here and y there, but it's really the same integral. So if we summarize what we actually have here, I'm just going to write this and then write that squared. So what we have here is quantity integral negative infinity to infinity e to the negative x squared dx. So times really itself, even though the second copy of that was written with y's, is equal to pi. And if we square root both sides, we're going to have integral negative infinity to infinity e to the negative x squared dx is equal to root pi. Root pi. It sounds like some kind of pie made out of beets or something like this. But here's the thing. You might say plus or minus sign. Well, don't need to worry about it because the thing you're integrating, e to the whatever is always positive. So this is the value. Now, this is actually a super important integral. Not so much for this class, but it's interesting to use the techniques of multivariable calculus to look at a very important integral in probability and statistics. So this is related to a thing called the normal curve, if you've heard it. If not, don't worry too much about it. I just want to show you a neat integral that is, now that we have this fact here, a very similar integral that's going to make use of this fact right there. So integral negative infinity to infinity of e to the negative x squared over 2 dx. This is a very famous integral, and if we just rewrite this ever so slightly, we'll have integral negative infinity to infinity. We're just going to do a little algebraic thing here. E to the, copy the minus sign already, and then for the rest of this, we're going to write in parentheses x over root 2 quantity squared. It's kind of a funky way to rewrite x squared over 2, but it works. Okay, dx. The whole point is now we're going to do a substitution. We're going to have u is equal to x over root 2, and du ends up being 1 over root 2 dx. Okay, the thing is, we're about to update this integral so that we're not going to have dx at the end. We're going to have du at the end. But the thing is, as x grows, u grows, because all you're doing is taking your x value and dividing by root 2. So this will still be an integral from negative infinity to infinity. But these are u values, so to speak, instead of over here where we had x values. But we're going to have now here, due to due to this root 2 in the denominator, we're going to end up with root 2 times e to the negative u squared du. Point being, we can bring out the root 2 in front. Yeah, we'll have root 2 times integral negative infinity to infinity e to the negative u squared du. And the point is, this integral right here, we just worked out. It's just written with x's up there. And so we're going to end up with root 2 times root pi, which is more typically written root 2 pi. So you might have seen this integral equaling this before, or perhaps another way that this is typically seen, just to summarize. So we just got integral negative infinity to infinity of e to the negative x squared over 2 dx is equal to root 2 pi. You may have seen this in a slightly different form by dividing by dividing by root 2 pi on both sides, and you'll have 1 over root 2 pi times integral negative infinity to infinity e to the negative x squared over 2 dx is equal to 1. Now with that 1 here, or if you want, you can push the number here on the inside. Let's do it. Integral negative infinity to infinity of 1 over root 2 pi times e to the negative x squared over 2 dx is equal to 1. Right here you have, again, don't worry too much if you haven't seen it before, but what you have underlined here is actually what's called a probability density function, because integrating along all possible values of this variable x led to 1. That's the full probability. So if you haven't done probability, don't let this worry you all too much. The interesting thing here really to point out is we took this integral, which is really impossible using Calc 1 or Calc 2 techniques, and by converting the double integral into polar coordinates, we got a value here. We got pi. That is the key deal.